The malonic ester synthesis is one of those reactions that is really only useful in some very, very specific situations. The malonic ester synthesis is used when we essentially want to do an alkylation of acetic acid. And the reason that we need this reaction is a typical alkylation is an alpha substitution reaction. We start with our carbonyl, we add a strong base such as LDA, and then we add an alkyl halide. The problem is that if you try to do this with acetic acid, of course, acetic acid, by its nature, is acidic. And so if you add LDA to acetic acid or any carboxylic acid, you're not going to form an enolate. You're not going to remove the alpha hydrogen. You're just going to manage to form a carboxylate salt. And so because of that, we need to have another way to do this. And that's what the malonic ester synthesis does for us. So the malonic ester synthesis basically uses a diester that comes from malonic acid. So here's malonic acid with a pair of methyl groups to function as the ester groups. And in this reaction, we add base in the first step, and then we follow that up with our alkyl halide. Now we can use base here because we don't have a carboxylic acid group present. So the base, as we would expect, will remove this alpha hydrogen. And this alpha hydrogen is really easy to remove. It's the hydrogen between two carbonyls. So very, very acidic hydrogen. So we form our enolate, and our enolate adds whatever R group we've added as our electrophile. All right, so far nothing unusual going on. As I said, we've literally just done an alkylation of a malonic ester. From here, though, and I'm not going to run through all of the mechanistic steps. These are steps that we've seen before. They're steps that if you need some review on, you can find them in the various places. But let's take this. And we lost our oxygen, so let's draw that in. What would happen to this if we added acid and heat? Well, that's a reaction we've seen before. We've seen it numerous times. These are the conditions for an acid catalyzed hydrolysis. What does a hydrolysis do? Well, recall that a hydrolysis will convert an ester into a carboxylic acid. Since the malonic ester here has two ester groups, it'll hydrolyze both of them. And so we end up with this diacid. Now for my next drawing, nothing is happening in terms of the reaction here. All I'm going to do is sort of manipulate the way that this is drawn. And we'll see why I do that in a minute. So if you look carefully at the way I've drawn this, and really what I did here was I took this carbon-carbon bond and rotated it. But right around here, and I'm going to erase that highlight in a moment so it doesn't distract from seeing where the electrons are moving, we have a six-membered ring. And so under the right conditions, and it turns out with a malonic acid, it typically only requires heat. We see the following happen. Carbonyl pulls off that proton, these electrons shift over, and that actually breaks that carbon-carbon bond. And as a result, we get what is basically an irreversible process that forms this new compound. Why is it irreversible? Well, our byproduct we kicked out was CO2. Of course, as soon as we form any carbon dioxide, it's going to bubble away and it's not going to be able to come back into the reaction. Now, we're almost done, but notice we now have an enol. Not only do we have an enol, we're still under acidic conditions. And under acidic conditions, an enol and most enols are going to, typically on the order of 99% or more, get converted to the carboxylic acid. This here is no exception. And so we go to the more stable carboxylic acid, which in this case, because of what our starting material was, we can now see we've sort of unmasked the acetic acid that we wanted. And so the overall net result of this reaction is that we managed to do an alpha alkylation of acetic acid. Again, we have to go through this more complicated route because of the reactivity of acetic acid, but now just to demonstrate it with some actual reagents, again, we'll use the dimethyl ester here. Don't need a strong base at all because of the dicarbonyl, so maybe we just add sodium hydroxide. Follow that up with benzyl iodide. And after the alkylation, we get to this point. Again, now we're going to heat it up with acid. We will initially get our diacid, which then rearranges to essentially lose one of the carbonyls, and we reveal our acetic acid. Again, acetic acid with the addition of the R group. So sort of a very specialized reaction, because again, we're typically only going to use it in situations where we need to add an acetic acid onto something. But in the situations where we do need to use it, quite useful reaction.